record this lecture. Maybe I would wait for another minute. So actually, I should start. Okay. So so welcome to the fifth lecture. Just wondering, have you guys have any problem with the lab sections or homework? Or you already submitted? Or mentally you already submitted? Or is this still here and not pulling it out into works? If it's already here, then it's okay. We still have some time. If you need extra time after this lecture, we can talk, and then I can try to do some troubleshooting. Again, we have set up the the office hour on Friday. We find a room there. I just know the number. I don't know the physical locations, but I make an announcement. So I guess we can find it together on Friday. Today I would like to talk about another type of parasiticity and the corresponding machine learning strategy to learn to actually create model for that. So I will cut it into two parts, and in this part I will talk less about the machine learning, but just talk about the major idea of how to set up the problem, and then in the next lecture we will talk more about the actual implementations, because that one it's a little bit more evolved. Okay, so we are here. So as I mentioned before, we have two lectures that are actually dedicated to more classical, so parasiticity modeling with a neural network, and then there's a corresponding paper. The lab 2 is actually already ready. I just need Ming to post it. He's not here right now. Maybe he's still putting it here. He told me he's ready. He did not tell me he's ready in the collab or here. So one of the case would happen, but I actually looked at it yesterday. It should be ready by today. So I will move the due date of lab report 2. Okay, today I just want to talk about a few concepts: the yielding point, the yield surface, the implicit representations of the yield surface, and the use of the level set or sign distance functions to represent the yielding. And then we probably don't have time for the in-class numerical experiments, but we can use the remaining time to answer questions about the lab report 1. Okay, so I want to first start with a code that I think is very true. I think God makes the solid, and then the devil are made by made the surface. So we are dealing with the surface. So we literally create a surface, but I won't necessarily think ourselves as devil. A Wogan Pauli is actually a very extraordinary physicist that won the Nobel Prize using some of the technique on the metaphor. So I guess he has the right to say that. Okay, so on the big picture, what we actually want to do is very simple. Let's say we have some data. It could be representative elementary volume data. Yeah, it could be a real physical test. And then provide that, we can use the difference between the elastic and plastic response to define the yield point. Then the question is, how do I complete a yield surface model? As we can see, a yield surface is actually like a criteria. You can think about it like you get a speed ticket. Okay, if you drive 80 miles per hour, you would get the ticket, right? So that would be a criteria. What it means is that if the velocity of your car, or more accurate, the speed of your car is actually less than 80, you're fine. If you reach 80, you are on the boundary of the legal limit. If you go beyond 80, which is possible, you're going to get ticket, right? Okay, so the yield surface is actually related to that in the sense that this is a criteria. But one thing that are actually interesting analog between the car and the yield surface is that at the car, you never see that I'm going to create a criteria if your velocity and the northwest and the east, sorry, in the north south and east-west direction is extend certain limit, you're going to get a ticket. It's the speed, right? Okay, so there's involve a parameterization process to convert these criteria into the scale. And that scale is actually the U surface, okay? You want something smaller than 0, and 0 is a scalar. So we need to actually representing the U surface in a proper way, okay? Just like the ticket, okay? So why did they use the speed, not the velocity? It's actually more convenient for the police to give you more ticket, right? So, okay, so here we're going to have a more rigorous discussion on that. Okay, so I'm just doing a very quick review on the plasticity. If you took a course from Professor Poha, you have far superior knowledge on the plasticity than me. And I would say that, so here I'm not trying to compare to that really wonderful course. I'm just going to give a quick review. Okay, so here I'm going to use the elastoplasticity theory, which is actually different than the last time where we used the recurrent neural network. I'm going to explicitly define the regions that are called elastic, regions that have no memory. I'm going to actually saying that at some point the material yield, okay? And when the material yield, it entered the regions where it have memory. And then at some point you're going to break, and we won't cover the breaking part in this lecture. And one thing that we mentioned last time is that in the if a material has a Parsic behavior, it has memory in the sense that if I actually loading the material from from the initial state to 4 and then I'm loading it, I'm not going to go back to the original path. So what it means is that if I cannot write the functions, that in that 1D, even in the 1D case, I cannot write simply a function that maps string to the stress or stress to string. Okay, even though the slope never becomes 0. Okay, because the path itself has an effect on the resulting behavior. Okay, so here I'll break the lecture into two. One is to determine when does that memory occur and how do we parameterizing that on set of memory events. Okay, and the second one is how to capture the revolutions. Okay, so those are related questions, but they are actually slightly different. Okay, when we talk about mathematically how to do that, and then once we figure out how to mathematically written it, we will use the convenience of the neural network to find the learn functions. Okay, so as you can see later on, the learning problem here is not special at all. It's just a classical neural network supervised learning. But what we can actually leverage is a lot of geometrical features that ensure that the model are actually behaving in a robust way. Okay, so now I'm going to talk a little bit about the basic of the plasticity. You can create path-dependent behavior mainly because of the microstructure or in some cases a nanostructure change, and that change is permanent. That can be due to dislocations, as you can see here. If I have this broad and then a part of it is actually moving, then I have a dislocations, and that dislocation will permanently change the configurations of the lattice and hence have a permanent deformations. Sleep and twinning could also be another possibility. For granular material, the reorganizations of the particle, the rotations can all lead to permanent deformations that can be accounted as a plastic deformations. One important characteristic between damage and plasticity is that when you load a material, you can both see degradations from the plastic deformations and from diffusive damage, but the difference is on the unloading. If you unload a damage model, the slope would actually degrade it, versus if you have a plastic loading, you're assuming that the elastic unloading are actually parallel to each other. You see this E? They are actually parallel to each other. Okay, so there's a fundamental difference between the damage and plastic deformations. Okay. Well, in real life, you won't get exactly parallel. So like you will get a little bit of adjustment. So but that is another story. So I'm going to go over the key ingredient of the plasticity model. It could be redundant for you, but here I'm going to do something more modulus than last time of the reinforced recurrent neural network. What I'm actually trying to do is the following. I'm going to tell you where is opportunity to perform some surgery. on a known theory with the neural network, and what is the benefit and the disadvantage of using neural network to write such a plasticity model. You can think about the previous lecture and this lecture as two opposite directions of writing plasticity model. The first one is that I'm going to give all the tough job to the machine learning, and if I have big data, I just let it figure it out with the advanced algorithm. Here, I'm actually more conservative. I'm trying to play the game in different way. I'm just figure out the path that I can put the neural network there. And if I'm not sure, I just maintain the more structure of the plasticity formulations, okay? So, you can make your own choice. So the world is changing. So you never know, maybe tomorrow, the ChatGPT can just give you the stress strain curve. So then we all lose the job and we can wait for the universal income from the government. That would be wonderful. But so far, before that, we can learn the machine learning for plasticity. Okay, so here we actually deal with a very specific problem. Okay, we actually just want to give in a strain history and predict the stress. And I would like to define the problem in a very restrict manner. We are giving the stress and the strain in the previous time step and the internal variable, as well as the current strain. And then what we actually need to predict is the new stress and the new internal variable, where the internal variable represents the history. Okay, so here in this lecture, we'll focus on these two, the yielding criteria and the parsic flow, how to using the neural network to generate those. Okay, so I want to just review what is a yield functions. I think how many of you have a basic idea of what is a yield functions? Okay, so I think that's good. I think I will be redundant on that, but here I think that I use that figure a lot, but here let me explain a little bit. Okay, the yield functions basically is a specific way to represent a surface, and that surface is like the speed ticket I talked about is a criteria to indicate some change. Okay, and here you can actually see that different type of yield functions are actually corresponding to different physics. And that I will talk about one by one, but long story short, I just want to point out the connections between creating a geometry and writing a yield functions, okay? So the yield functions have a physical consequence. For example, von Mises stress would have in the hydrostatic axis, where sigma 1 equal to sigma 2 equal to sigma 3, this line, 1, 1, 1 line, would actually, if you actually cut a pin on the von Mises U surface normal to that 1, 1, 1 axis, you will get a circle. And that circle actually doesn't change the radius. So what the physical mean is that the von Mises is independent of the pressure. As I actually visit through the 1, 1, 1 point, I'm going to simultaneously increase the same amount of pressure or principal stress, and hence I would not, and along that axis, the radius is the same, which meaning that they're insensitive to the pressure dependent. The other way to the improvement by Juger and Prager is actually introducing the pressure sensitive, and hence you get a cone instead of a cylindrical object. Okay, so what the cone mean is that for a material that I actually have more pressure, I need more directory stress to trigger the yielding, and this is called frictional response. Okay, the more the friction angle it is, the more dramatic you see the yield surface open up along the hydrostatic pressure line, and then you would see more pressure dependent. So this is called this is the simplest pressure dependent model. And for metal, you can also see yield surface that are not continuous. You can see a sharp corner. This has actually happened a lot in crystal or in a metal or in polycrystal, where the plastic deformation can be triggered by discrete events such as slip system getting activated or grand boundary movement. That also have a physical meaning in the sense that this is actually the corner represent a very discrete event where if you're loading it very close to the corner, you have two really feasible slip system or passing flow that are equally valid. And then you can see that the rest of the U surface are actually manipulating the geometry to incorporate more physics to it. And then you can incorporate more physics by the following way. One is to increase the complexity of the geometry. Okay, you can see that from the Thorson-Kamke to the von Mises, I actually make the U surface a little bit more evolved, just to give me a taste of a more complex passing flow. Okay, I can actually at the different combination of stress, if it yield, I can have a different predictions, and it can and I can create a different type of behavior. Okay, so you can think about it as so the discovery of the U surface itself could be considered as a discovery of new geometry. Okay, so this is actually one of the inspirations of what we're doing. So just a quick review, U surface. In a U surface, you need a parametric space. This is actually, for example, a QP space that represent the directoric stress and the volumetric stress. There are, at any point, the point actually can be classified in three different types of behavior. One is actually elastic range. Okay, so elastic range is actually anything in the U surface. I think it's actually very easy to understand. If I load the material, the stress is not enough to yield, then I consider the thing have no memory. So in that orange-ish domain, the material have no memory. And then at the yielding point, when the stress is touching the U surface, I will consider the material is yielding. Anything outside is impossible. Okay, so that's why that's another major difference between elastic and plastic. If you have a linear elasticity material, and if a linear material exists and always remain linear, you can get any stress combinations. Okay, any imaginary number, maybe 1 trillion gigapascal, you can get it. Okay, because it's linear, you have a mapping, you can just have some very big stress. For plasticity model, there is only a range of stress you can achieve. Okay, taking account of the hardening, because ultimately the material may fail. And then that combinations is determined by the plasticity model. Let's see. So a plasticity model basically have the following ingredient. It would have an underlying elasticity model, which we can assume is linear. If you have a metal, aluminum, something very ductile, it doesn't have that much non-linearity, or you can consider it as a nonlinear material, and you need to actually train it or actually deduct it. And then there's a yield criteria that tell you when the material is yielding. And once the material is yield, then what actually happens is that the strain would be decoupled into the elastic part and the plastic part, and how the plastic part grow would affect the stress you get, because the plastic part in the small strain theory, you have the stress equals to CE double dot, the elastic strain only, and then that would be active. I'm assuming linear elasticity. And then that will be equal to the total strain minus the plastic strain. Okay, so and the underlying assumption is that the elastic strain and the plastic strain actually partition the total strain. Okay, so the more plastic strain you have, the less stress you have, if the elasticity model is actually stable. Okay, so the flow actually deduct what kind of how the amount and the type of the plastic strain you get. And they are actually could be controlled in various ways that we will talk about. And there's another ingredient, which is actually the hardening and softening of the plasticity model that tells you for plastic deformations or some historical physical attribute, how do I evolve that yield criteria? Okay, so in a sense, like a parking ticket, if you cross the state, the speed limit may be different, or in a highway or in a local, that is different. So the locations could be a parameter that you can consider as your hardening or softening law for the parking ticket. Okay, so in that analog. Okay, so the yield functions, this is actually the yield functions, and the yield function is not the yield surface. The yield function is a one way to represent the surface in an implicit manner. Okay, and the majority of the yield surface are actually represented in the implicit functions. So as I mentioned before, you can actually write a J2 parsiticity. This is one example of ISO U surface that doesn't have backstress. So you can actually enlarge the cylindrical object, making it smaller, but that's it. And you can control that by changing the radius. So the change of the radius will be the hardening law. The entire criteria would be the U stress. And the passage flow is actually not given here. It could be obtained by a different law. But here, one thing that you can actually see that could be quite interesting is that depends on how I parameterizing the U surface, meaning that how I write the U surface in terms of what I have different level of complexity. Okay, so for J2 parsiticity, the smartest choice is to write it in terms of J2 because I just have one dimensions. Okay, I just need to control the J2 that I just need to control these parameters smaller than the Kuiper, and that's it. And then another choice is use the principal stress. Another choice is write the entire stress component. They're all equally valid. The difference is that when you compute a gradient, okay, you will have different kind of complexity. I just want to mention that we cannot, in general, expect the U surface to be smooth. Okay, and the non-smoothness of the U surface could be a big problem. This is Zuckerberg U surface, and one thing you can actually see is that you can write the U surface in this particular way, and you cannot write it within one equations. Okay, you have to have the 3 different criteria, one criteria for 2 different phase, then you cover the polygon. Okay, you see what I mean? Why is that? Because you have that corner. Okay, and it's actually not so productive to write one function for something that have a corner. So you may better off write the equation. So the idea is the following. I'm going to, the actual U surface actually on the piping could actually look something like this. Okay, it's actually have those regions as well. Okay, it goes to infinite. Okay, but I'm just taking that they have to be included in all the criteria. Okay, and you can easily see that if it's not smooth, it will become much harder to detect whether I'm inside or outside because I have to check all of them one by one. Okay, you see what I mean? And to check that it's elastic, I would actually have to check, am I actually in between these two, in between these two, and in between these two? If I'm actually all inside, then I'm actually in the elastic regions. Okay, so and again, you can see that you can use the parametric trick to make the model a little bit easier to understand, and then we will talk about the choice of the parameterization later. But what I want to mention is that the choice of the parameterizations, how I actually express the U surface is actually important for handcraft U surface and the machine learning U surface. Okay, so before you solve the problem, the most smart way to do something is to figure out what is the easiest way to do something. Okay, or like what my student would like to say, the less implementation of something. So sometimes it's actually the best solution, right? Okay, so I just want to point out that there are other U surface. For example, you can create a micromorphic U surface, but then that becomes really hard to write it manually. You can see that there are 27 of this boundary. I'm not smart enough to come up with an equation that actually bound all the point on the U surface. If you're smart enough, let me know. I would like to hear what is the equations, but you need to actually capture all those shapes. Okay, so what I want to say is that whether the machine learning is useful also depends on the dimensions. Okay, for small dimension and simple shape, because we already wired to have some simple shape implicit function in our mind that we can use, there's no point to actually write a machine learning parsiticity model, except for writing paper. But for high dimension is almost necessary. I just don't see how we can do it. Okay, so what is the passing rule? Flow rule. Passing flow rule is like what I'm talking about. It actually governs what type of passing string I get. Okay, so for J2 parsiticity, I get a circle. And then that circle, if I use something called associative flow rule, the U surface is actually all pointing outward. Okay, if we look at the cylindrical object, Okay, what I actually find is that I'm going to point it all out on that principal stress space. I won't point it in here. I know I won't point it in here. Okay, so why is that? Because in this axis, I should have no component. All the arrow are shifting orthogonal to the hydrostatic thing. Orthogonal, geometrically orthogonal, meaning that they're independent of that. And what it translates to is that it would actually have no volumetric change. Okay, because in this 111 line, sigma 1, sigma 2, sigma 3, I'm actually shifting straight. So this is actually 45 degree, and I'm just going up on that. And then along this normal line, I would actually have no volumetric component. Okay, so there are multiple ways to derive hardening rule. The plastic flow rule. The most popular one and the simplest one is use associative flow rule. What it means is like what we talk about. I just simply using the U surface also as a requiem to manifest the different mode of the use stress. Okay, notice that in my opinion, it's only the directions of the plastic flow that matter. The magnitude of the gradient doesn't really matter, because if you actually predict the wrong gradient, you will get correct in the plastic multiplier. If you know what I'm talking about. Yeah, you have a 2U surface. If I have F equal to 0 and I have 2F equal to 0, that's what I mean. If you compute the gradient, you would find out the exact same plastic model. The only difference is that your plastic multiplier would be actually smaller, okay, or actually bigger because of that. So what you care is the magnitude. Choice number 2 is to cook up another potential and use that potential evolve also with the internal variable, and then that internal variable and then that one will give me more freedom to introduce something like the von Mises stress. Actually, for the granular flow people, they like to do that, but for geotechnical engineering people, they will really hate it. Is that, or in computer graphic, I actually see that in this lead, they actually see that they have a von Mises U surface, but their plastic flow are actually not normal to the hydrostatic axis. It's actually like that. So why do we do that? Because then I need to come up with Drucker-Parker cone as my plastic potential, but the advantage is that when I shear the material, I can get some dilations. Okay, this is actually a trick. But the problem is that I have to write the plastic potential. Okay, so this is actually also create more burden for the inverse problem. And as I said before, if you have associative flow rule for J2, that's fine. Okay, if you're actually a non-associative flow rule is just a plastic potential that also is a cone but a little bit bigger, that is actually fine. But if you're actually dealing with it in a very high dimensional space, then you actually need to create 2 geometry. That would be almost impossible. So my recommendation is that if you can avoid, don't do that. But in soil mechanics or in rock mechanics, this is actually very popular. Just simply because the rock behavior have a lot of microstructure involvement that are really hard to capture geometrically. You cannot. The typical rock mechanics, the U surface are really simple. They are not create that detailed plastic flow, so you're actually using that. Okay, so there's another thing that are actually also very popular that are actually kind of like a dark art, but well, I shouldn't say that. I think the lecture is record, but it's a generalized plasticity. So what I actually mean is that I don't even have a plastic potential. I just cook up some corrections from the plastic normal, okay, from the gradient of the stress. Okay, so I would actually say that I would actually grow the plastic strength in this not in this direction, but I will actually deduct a rule so that I can change the direction a little bit to create different type of plastic flow. Okay, so I don't need to write a potential and I don't need to do the gradient. I just create the corrections. Okay, if you correct too much, you may violate the thermodynamics. That's another story that really dedicated, but those are the 3 choices, regardless of whether you use machine learning or not. Okay, so hardening law is actually another ingredient. Okay, just bear with me. This is like a cooking show. I just show up all the ingredients. There's a turkey, there's a potato, and it could be quite boring. But the hardening is actually another one. It tells you the governing revolutions of the yield surface according to some history of the parsic string. Okay, so in the history, if you look at international journal or parsiticity or a lot of journal, what they actually did is that you either write a new yield surface or you write a new hardening rules, or you do a combination of both, or you just do a new combinations and then you can write a lot of paper. Okay, so people, but the long story short, if you take it out from the big picture, what people did in the last couple of decades is to define new hardening rules, and actually new yield surface based on some geometrical inspirations. Okay, I think we all know in our parsiticity class what is isotropic hardening, what is kinematic hardening. The geometrical inspiration is that I make the yield surface bigger whenever I develop the parsic string, so that next time I'm loading it, I would actually require more strength in order to reach the yielding. I can actually also make a kinetic hardening. If I actually loading it in the tensile direction, next time I would actually have a premature yielding in the compaction directions. Or I can actually increase the yield friction angle. I can actually rotate it, etc., etc. You can find tons of it. Just type hardening law for parsiticity. Okay, so now this is a major ingredient, and how do we put it together computationally? I won't talk about the theory because that is not a parsiticity course, but the long story short, the crush course would involve a return mapping algorithm. The way to write the parsiticity model is the following. I would actually assume everything is elastic. Every increment is elastic. I'm going to violate the law a little bit or maybe a lot, and I'm get to the child space, and then I actually using the flow directions, okay, that I actually determine to give me the guideline of how much correction I need so that I reach the yield surface, okay? Now, this is for perfect parsiticity, it's easy because the yield surface is actually already fixed, and then you just shoot it up and then go down, okay? But when you have hardening and softening, this thing is dynamic, so when you're shooting it out, you need to figure out how much does the yield surface need to move, and then you need to also matching them, okay? You need to kind of have a kiss between that stress state and the yield surface. Okay, so that mathematically will lead to a system of equations. I won't talk about it too much, but then long story short, I need the parsic corrections. You can actually see Ronnie's book, parsiticity computation for more details, but usually there's few ingredients. One is the first one is the parsic corrections, like what I'm saying. Okay, so I'm going to for the linear elasticity, I'm going to write it like this. Okay. And then I'm going to write that if I know this, and then I know the change, what I actually need to do is actually, that would be the n+1, right? And the parsic strength would be actually also equals to the change of it. And then that change of it, the delta of epsilon E n+1 is actually equals to the delta lambda times the stress gradient. Okay, so I'm actually, so this is in this case, this is a flow through. I'm using the normal vector to tell me how much I need to go down. Okay, and then the lambda is just the magnitude. I'm already fixed the direction. I just tune how much magnitude of lambda so that I can hit that exact yield surface. Okay. And then I need to everything to be correct. So I put it into a system of equations, and then I solve the Newton-Raphson algorithm. Okay. So the hardening law is governing, if you think about it like a cartoon, the hardening law is governing how the yield surface is moving or evolving. And then the delta lambda is tuning how much I'm actually going to hit back onto the yield surface. And then the consistent equation is to make sure F equal to 0. Okay, if the material is yielding, then the criteria should, if you violate, if the material is yield, you assume F is on F equal to, your stress is on F equal to 0, not F smaller than 0, not F bigger than 0. So you're enforcing that, then it will magically come back with the new stress update that actually give you the output. Okay, so this is the classical ingredient. If you actually need a refreshment, you can look at the textbook. Okay, so here, before we work on the machine learning or the level set, I just want to talk about that again. The most important thing that dedicate 90% of the difficulty of the problem is the choice of the parametric space. the parametric space is very important because it tells you the symmetry. It depends on how you're parameterizing it. You may get a different, you may get a more obvious symmetry you can observe or very subtle one. And basically those are the choice. You should actually choose the choice that are as small as possible. If you can actually pick a small dimension, don't pick a large dimensions, because that would actually, the reason that you can actually reduce a parameter is because you already inherently enforce the symmetry. Okay, so if you actually unnecessarily expand the space, then you need to enforce the symmetry back, which actually translates to you need to add the additional constraint to enforce the symmetry back that make the local Newton-Raphson's algorithm actually bigger. Or you can violating that, just pretend that it doesn't exist. So that could also do trick, but it's not recommended. So you can actually see all those different choices. And I just want to mention that there's a few criteria on picking the parametric space. You want to make it as small as possible, but at the same time, you have to make sure that all the parametric space are orthogonal to each other. Okay, I think this is obvious, right? So what I actually mean is that you can actually come up with some, you can come up with any combinations, but we cannot create a space by saying that I create a sigma 1 and then a sigma 2 here, and then I write sigma 1 plus sigma 2. Okay, that would not work. Okay, you see what I mean? If you do that, what will happen? If you actually create that basis, okay, and then you write the yield function, what would happen? Okay, so let's say I want to create a circle. Okay, I want to write a hormesis using this space. So what will happen? Okay, what would happen? There, can you guys imagine? Well, maybe actually sigma 1, or maybe I already have the J2, but I actually want to add sigma 1 and sigma 2 because I have nothing to do and I just want to entertain myself. So what will happen? If you do that, they're not orthogonal. So that means that there are multiple expressions that can probably fulfill the same criteria, and then it won't work. Okay, so the first thing to check is that whether they are actually orthogonal. Okay, but this is true with stress. You know, sigma 1, sigma 2, sigma 3, they're orthogonal to each other, right? Okay, so the orthogonal is necessary ingredient when you pick the basis. Okay, things that are actually not so true based on the Harding law. For example, do you know the porosity and the fiber tensor component, are they orthogonal? Okay, that becomes less clear. Okay, but the orthogonal is actually necessary to constitute the parametric space. I want to say that I'm just cover the most common yield surface. Typically, we use the stress and the internal variable to write the yield surface, like the J2. J2 is a stress measures, and I just put the radius, and then the radius is actually could be a function of the parasitic strength. But they are string-based yield surface, string-based parasiticity. You use the principal string to write the yield surface. Yield surface that are of higher order, like our long local. I will use a long local stress measure to put it into the yield surface. Or the strength measure or rotations, those more exotic things actually also occur. Okay, so and then just want to give you some idea. So in the parasiticity course, you probably already know that the majority of your homework or your final, except the elasticity part, will be only on the isotropic elasticity. There are basically two choices of the writing isotropic elasticity. You can use two invariants or three invariants. In the three invariants, or you can use the eigenvalues. So in the eigenvalues, principal stress space, what you're actually assuming is that for a given principal strain, I would always get a principal stress. It doesn't matter where that principal stress happened. The combinations of the principal stress would actually be identical. The orientations of the principal stress, on the other hand, would be actually actually pair with the principal direction of the strain. Okay, so that's it. And for metal, another common choice is that we will use the piping. Okay, so piping is obtained by actually changing the perspective of how we wheel stuff. Okay, so basically you can do it with 2 rotations. Okay, so you see that this is rotations, because if you look at the column vector, the L2 norm of all the column vector component are 1, 1, and 1, right? Okay, so that constitute what physical mean of the first vector is that I'm going to hold the sigma 2 axis, I'm going to rotate by 45 degrees. Can you see that? Okay, because I'm actually, so this column is 0, 1, 0, right? I'm not going to changing that. Okay, so I'm going to hold sigma 2 constant, and then I'm going to adjusting the ratio. Now I'm going to adjusting that by actually creating a new coordinate system that actually have the old sigma 1 times this, and then the old sigma 3 times this, and I'm going to rotate it, and they are in the equals weight. So I'm basically just going to rotate it by 45 degrees. Okay, so the next one is actually not 45 degrees. Can anyone tell me why? Yes.
I mean, are you talking about the transformations on the far right?
Yeah, this one.
Yeah.
Okay, it's 1/3. Why is that?
That correspond to, it's 30 or 60 degrees. I'm trying to think which one.
Yeah, okay. So I'm literally doing that in order to reach that 1, 1, 1 line. Okay. In order to reach that 1, 1, 1 lines, in order to wheel from the orthogonal to the piping, to the hydrostatic axis. The hydrostatic axis is the axis where sigma 1 equal to sigma 3. I want this to point to my eyes directly. I want to look at it this way. In order to actually do that, I first rotating this into these directions. Okay, that is 45 degrees on the 1-3 plane, right? So that's why you have this. And after that, you see the length of this. What is the length of this? Sorry, what is the length of this line? Okay, yeah, actually, yeah. So if I actually want to reach that corner, I will actually have a different angle, right? You see what I mean? And then that would actually lead to that split. Now in the second action, I'm first rotating by 45 degrees, and I'm holding the first axis, and I'm rotating it in this way so that I can actually get the eyes view that are pointing to that. Why is the advantage of doing that is that if I actually have a 3D object and it doesn't evolve in the hydrostatic axis, I can actually get rid of one coordinate. Okay, do you see that? Okay, what happened in this new coordinate? Sigma 1 pi prime and sigma 2 pi are actually the x and y here, which is actually corresponding to this axis and this axis, and sigma 3 phi is actually pointing towards you, or pointing towards me. Okay, so if things doesn't change in the hydrostatic axis, I don't actually need to care about sigma 3. If it does, I can still have an advantage by actually putting a sequence of 2D contour to represent the 3D to actually keep track of how the sigma 3 is actually obtained. But why do we want to do the piping? Has to do with symmetry, because that helps us see the symmetry more easily, or actually from the pattern, you can actually get the inspirations for the material that has symmetry. And hence that is actually very popular for crystal material that are actually have a lattice structure or crystal that inherently have symmetry and doesn't have pressure sensitive. Okay, so our mechanics people are actually really good at actually leveraging the symmetry to actually make a better model. Okay, so this is actually from Steve Jobs. I don't know whether you see the first iPhone presentations. I think this is when he presented the first iPhone 1. This is actually many years. I think you just born by that time. But I'm already old enough to remember. And what he actually talked about is actually all those Nokia, BlueBerry thing. What is the problem? Okay, so why are they doesn't sell, and why they are actually only captivate a very specialized customer? Okay, is this a bottom? Okay, what is the problem with this bottom? Okay, for people that are working as an accountant, you need a bottom set of 1. For the people that are lawyer, you may need a different button. For the people that actually deliver food at Uber, you did need a different button. So how many different type of button you can actually create? Okay, so the infinite amount of thing that you need to customize. And once you write the model, next time, let's say I deal with aluminum 7079, and next time I deal with aluminum 7076, I have to actually create another rules. Okay, you see what I mean? So I'm not criticizing people writing that. I'm just saying that it's actually very difficult to actually adjusting it every time. So it go back to the inspirations from the CEE316. Okay, is it a possible way to create a skeleton key so that I can manifest all those shapes without actually handcraft or deduct all the things manually? Okay, is it possible? So this is actually the motivations of what we're trying to do here, and actually what I'm trying to do. So okay, so is it possible? Okay, do you think it's possible? What do you think is the right way to do it? You see a lot of examples, right? Well, Mises, Prager, hardening law, what are they have in common? Okay, so just think about it. What are they share? What feature do they share? And then what are the features you need to add it to create a specific model for steel, for rock, for, right? You see what I mean? So how do you get rid of the bottom when you want to write a model? Okay. You see what I mean? Okay, so one of the bottom is actually the control of the shape and the revolution of it. And then the level set, it turned out one way to actually deal with it is just thinking of it as a level set. The most generic way to actually manipulate every different shape, which we already know many years ago in computer graphic, modeling fire, water interface, is using level set. Okay, level set actually is a generic way to represent the surface. And interestingly, they also use implicit function to represent a boundary. Okay, so we just already, so what I'm saying is that we already have all those ingredients from other field. We just need to put it together into the plasticity, and then the goal is to hopefully we don't have to handcraft everything every time we see something. We just need to see the new set of the data, think about what is the right way to create that shape, and that's it. Okay, you see what I mean? So that's the goal. I think that I'm kind of recycle the figure a little bit, but here I'm going to reconsider the U surface. Okay, I'm going to do some surgery on the U surface. I'm going to maintain the principle that the sigma, the F greater than 0 is not possible. F equal to 0 is yielding, and F smaller than 0 is elastic loading. And then I would collect some data. Okay. So here I would imagine that we have a physical experiment, and then actually we start with low stress, and then I'm going to actually to save time, I will start the loading it in the boundary of the triangle, and then I'm going to loading it in all the different radial directions until it yield. Okay, so this is actually a crystal material. So eventually, when it yield, I just stop the loading, and then I'll take the initial yielding point. Okay, so if I get that, then I will actually have a F equal to 0. And then if you actually try to using this as a source data to train a supervised functions for the yield surface, so what will happen? So the yield surface is actually a functions that give you values everywhere in the domain. Now I'm giving you one contour. So what would happen? Okay, so do you understand what I'm saying? So I'm going to write a functions, and the yield surface could be as simple as the yield surface can be as simple as simply this yield surface. Okay, now this one have values. Okay, I'm going to learn that, and then the yield surface is only a scalar. I can do it in any supervised learning, and then I can do it. And then the problem is that in this particular example is more extreme. I only give you the value of J2 and the Kuiper when F equal to 0. I don't give you any other data. Can you write the functions? Okay, I only give you one point. Okay, in that J2 space. Okay, can you write the functions? Okay, I give you the boundary. Okay, nothing else. I cannot write a function, right? Okay, so I need the entire value for the entire space, not just one point. or one boundary. Okay, like if I actually want to solve like if I actually want to understand the entire landscape, but I only have one contour f equal to 1 or f equal to 0. Okay, so how do we supplement the rest? Okay. So one thing that are actually important is actually to think about the usage of the plastic model. You actually don't care about the values of the U surface inside the U surface. Okay, if I put the substitute the stress, I just need it to be smaller than 0. And whether it's minus 1 billion or actually minus 0.05, I probably don't care because I'm not going to activate the correction part, right? It's a binary algorithm. And I also don't care about things that are actually greater than 0, because if it is greater than 0, I just need to matching it back to 0. Okay, what I actually don't want to mess it is the gradient and also the f equal to 0 contour. Okay, this is actually the inspiration because all the other number are never used and they make up. But then the f near the neighborhood, the gradient part, on the other hand, is actually important. So that's the only thing I need to preserve. And with that, I can actually create any implicit function that give me f equal to 0. I can get the same elastoplastic response. So I don't care. So that gives me some degree of freedom in the sense that what we have is just a contour, but what we need is actually to create a learn functions that are as simple as possible. One of the simplest function that I can think of, but there could be other choice, is just to assuming that this is sign distance functions. Okay, so I'm going to explain what is a sign distance function, but what actually we actually want is to simplify the supervised learning so that I not only have the benchmark data on the boundary, but I also have the boundary contact. I also have the data everywhere, and then that would actually simplify the supervised learning. You know what I'm saying? Okay, then I would actually create a very robust U functions with the minimum complexity in terms of the shape. Okay, and notice that again, I only need the orientations on f equal to 0 and the magnitude of f equal to 0 right for the right combination of stress. So this is actually the idea. And then I'm going to actually create a sign distance functions for, how many of you know what is sign distance functions? Okay, so okay, I may explain the redundant for you, but I hope you don't mind, or maybe I can get it wrong. Okay, but anyway, long story short, the sign distance function have the following property: at the boundary, that scalar function go to 0, just like the U functions. If it U f equal to 0, right? It's like indicator functions. If it's actually inside, then it could then it will have the opposite side of the U functions. Notice of the sign distance functions like this one. If I want to represent that boundary, okay, the circle or this funny shape, I would introduce level set values. And that level set value would actually exactly give me that inside that it will be positive, outside it will be negative, inside will be negative, outside will be negative. But not only that, one important property that simplifies that contour is that the norm of the f, the gradient of the f have to be equal to 1. Okay, so that means that the change are actually graduate along with the normal directions. Okay, you see what I mean? If you look at the contour, that means that if I have a 0 contour f equal to 0 equal to here, then the sign distance function will actually give me the nice contour that looks like this, and then this distance are actually all identical. Okay, it won't become shorter or longer. That would be a sign distance function. So it's just a way to actually recognize the entire pattern. Okay, so, and then we can do the following. In the plasticity, this is a very simple trick. Okay, to actually create a sign distance function, what I actually did is to identify 3 sets of data, the data that are on the boundary, f equal to 0, the data that are inside, and the data that are outside. Okay, so how do we do that? Let's say I have a point cloud and I start with somewhere outside. If I actually looping it in the XY component, I would actually either touching the boundary in an odd number or in an even number. Okay, so if I'm outside, I'm actually cross the border, I will be inside, right? If I cross the border twice, I will become outside again. If I actually cross the border, I will be inside. So I just need to count I just need to have a point inside and a point outside And now I count whether I would have even number of crossing the boundary or odd number of crossing the boundary, and then I can identify whether the point are inside or outside. Okay, that is actually one simple trick. And once I have the inside and outside trick data, I actually can start. This is actually a geometry just for cartoon purpose. And if I have a binary functions that indicate what is inside and outside, I just need to solve a level set functions to enforce the unit of f equals to 1, and I will get these functions. Okay, so this would be, then I would use the point cloud of these level set functions to actually learn the use surface of a different point. Okay, so mathematically, from the level set theory, this is called reinitialization problem. I'm simply enforcing the unit of the gradient, the L2 norm of the gradient equals to 1. And then this is actually the equivalent behavior of that if the dot product of it equals to 1. Okay, which probably makes sense. If the inner product equals to 1, the L2 norm equals to 1. And all those things, and then the gradient of the yield function are orthogonal of the speed function are actually orthogonal to this. Okay, so I would actually talk about a specific way to do it. Okay, so this is actually, again, not from that much from machine learning, but from the level set. I can simply minimizing that energy norm to achieving that. What I'm actually trying to do is that I enforce the gradient to be the norm of the gradient to be equal to 1. That actually meaning that I'm actually trying to make the space all 1 and just control the space. And then at this boundary point, G is actually a spike functions and the boundary. I want to make sure that the gradient doesn't change. And then also on the boundary, I also want to forcing the f equals to 0 doesn't evolve. You understand what I mean? So mathematically, I'm actually painting the boundary and then moving the thing inside and outside. Do you get the idea? Okay, so you solve this problem and you will get this. Now, if this is too complicated, there's a backdoor to do that. You just need to open MATLAB and type side distance transfer, and then you can get the sine distance functions. Okay. So which way are you going to do? Are you going to solve this or go to MATLAB and type sine distance transfer? You can make your own choice, but the sine distance transfer only works for 2D. I think there's a 3D implementations, but it won't work for n dimensions. But if you use the MATLAB to do your homework, that is perfectly fine with me. But make sure you pick the right norm, okay? Because the sine distance function doesn't necessarily corresponding to the L2 norm. It can corresponding to the Manhattan norm, for example. I don't know. Do you guys know what is a Manhattan norm? Yes.
Oh, no, I was just raising my hand to say.
Oh, you just want to say yes, okay. If you're living in Manhattan, it's kind of implicit. It's actually related to the cost of taking a taxi, because in Manhattan you have a grid system. Your true cost of the taxi is not that much depends on the Euclidean distance, but the Manhattan distance we translate to the how much x and y I need to cost in order to reach the distance. Okay, so if you go to New York and you don't have time, you want to estimate how much it costs to do something, use the Manhattan distance, don't use the Euclidean, it will make no sense. Okay, so anyway, so that's the two choice. And then once we did that, we actually have a very simple problem. In the last lecture, we talked about the brute force approach using the reinforcement learning. I would say that is a black box, but you can also make it a gas ball or add some ingredient, which we will talk about that later. But you can actually, this is a very two different fundamental differently approach. One is that I'm going to use a very powerful architecture. I'm hoping that I have some powerful gadgets that allow me to achieve the task, and I'm not doing any manipulations. Okay, I'm just throw all the stress strain data and then to the architecture, and I'm hoping that the AI is smart enough to doing with it. And then here I have a more cynical view. I just thinking that the AI is just a regressions processor. I'm control everything in details, and then in particular controlling the geometry, but I can actually get more control. So now this is actually what this lecture and next lecture is about. I'm not so sure where the future is like, but it's kind of moving into that directions. So until then, we can using this to make a living, I guess. or maybe just me. I'm not sure. Anyway, so the training itself is actually just a classical supervised learning with the exception that now I'm actually simultaneously trying to train the yield functions to be matching the data point, and I'm going to use all the data point in the level set inside and outside also as the training data point, and so that I actually would have more data. You can try that. If we train a neural network that actually only have f equal to 0, and then you try to train it, you can get the learn function, but it will be very unstable. Okay, you see what I mean? Because in order to actually make f equal to 0 at a given point, I have so many different patterns that can let me achieve these tasks. So it's actually not stable, and you will find that you can get many different solutions. Or if you actually do that, you may find out that you may also have hole. Okay, you see what I mean? So because actually I just care about f equal to 0, right? Here I have no control, so I can as well have f equal to 0 here, or maybe in a line, right? So I actually need to clean it up. That's why I need the interior and exterior point. Then what I actually need to do is to introduce the gradient. Now, this is actually also something interesting for those of you who already took the plasticity, is that if you actually can find a way to successfully train these loss functions, okay, if you're actually using the plastic flow measure instead of the stress gradient of the yield surface to actually train this, if this is successful, what indicate to you is that by actually creating a more compact shape, I actually don't need the non-associative flow rule. You understand what I'm saying? Because if I actually don't use the actual stress gradient, I use the plastic strain, and then I can still manage to completely rewrite the f equal to 0, and then the gradient is also matching the plastic flow. There's no point for me to cook up something that doesn't fit the normal directions. Okay, so I can get rid of the non-associative flow. If not, then that means you may want to actually introduce another change on the plastic flow. And the plastic flow I will recommend is the following. I actually could find a case where the yield surface look like that, but the plastic flow is actually more smooth. I actually don't know why for the microstructure, but then the important thing is the following. If you change the plastic flow, you may want to change the yield surface first, and then using the yield surface as the initial learn function to change the change to get the plastic flow, other than changing it with arbitrary shape. Okay, because the plastic flow have one problem is that you only get the gradient data. Okay, you think out, you know what I'm saying? From the mathematical world, you would actually have the scalar value of the plastic potential and the gradient of it, but from the physics world, you only get the gradient. Okay, which could cause some stability issues. Okay, so we just want to talk about the level set functions in more details. I'm just using a piping as example. I will have all the stress component. I'm going to consider only isotropic material, and I'm going to only consider isotropic material that are not pressure sensitive. So that would actually reduce my coordinate system into two. And then I actually want to solve that functions to actually obtain yield surface. So if I actually obtain the yield surface sign distance function, it would actually look like this. Notice that compared to the classical yield function, I swap the interior and exterior. Now the interior is actually negative, and then the exterior is positive. The reason is the following. I just want to using it as a yield surface, and you want the yield surface to be smaller than 0 when it's elastic, right? Not positive. So this is just for convenience, but you can flip-flop it. It's actually not a big problem. And then we would be processing to have the sign distance functions, and then we would actually obtain a yield surface that have gradient equals to 1. Like what I say, if you can also enforce the sign distance instead of a sign distance function, you can actually enforce the gradient equals to 2 or to 3. Okay, it doesn't matter, but what you would actually see is that you will see a different passing multiplier. Okay, so mathematically, your plastic strain, your change of the plastic strain, the change of the plastic strain is actually determined by the flow directions, which is the gradient of scalar functions, either f or g. and then that will give you the entire passing string increment. So this one is actually a second order tensor, and this one is just a scalar. So mathematics, so the physical connection to that is that this part gives you the mode. Okay, if I have a circle, I know that it's going to change it into oval. Okay, with this aspect ratio, I don't know how big, how much it would have, but then I can actually control the magnitude using this. This is actually a scalar. Okay, and this is actually related to the magnitude of the plastic flow, which you would actually get from solving the system of equations. So if you actually pick a different sign, different values, what you would actually have is that you would get a different passing multiplier. So in answers, sometimes they would have a U surface that are not sign distance function or have some funny magnitude, and then they would just normalizing it in the implementation. So you kind of get the same thing. So in general, I just want to show that you can get any different shape. One thing that you may notice is that if you use the level set to actually train the data, you would actually need the data everywhere, not just in the yielding point. Okay, so and this is actually how to create a very stable U surface, and that could be important for the evolvement to train the hardening and the softening. When you have the hardening and softening, this U point, you can consider this point are actually moving according to some passing flow, okay, or plastic hardening law, and you don't know how does it flow. So you actually, but you need all the data point to be moved accordingly. Okay, so this is actually the pre-processing step to create the training data. Once you have the training data, the learning is actually pretty simple. Just use the sober learning, and then you can get a shape that are actually ready to put it into the finite element. The next thing I want to talk about is actually the evolving. The level set representation doesn't only give you a way to actually simulate to represent the U surface. It also helps with the evolving the U surface. Okay, so this is Hamilton-Jacobi equations at Northwestern. At Stanford, I heard that it's only called convections, but I'm not sure. But anyway, so what actually show is that this is actually the level set functions. This is actually the gradient, and then V is actually the vections velocity that carry the level set to move. Okay, it's like yeah, if you know the convection term, is actually driving that level set to move. And one thing that could be simplified is that we would actually assume a stationary flow. This is called speed velocity functions, and F is called speed functions. Like the parking ticket, the difference between velocity and speed is that speed is the magnitude, is a scalar, and velocity is a vector. Why do we actually write that? Is the following. In U surface, you don't really care about the tangential flow, you only care about the normal part. You don't need the tangential flow because in the tangential direction of the U surface is all zero. Okay, and you don't use any tangential information inside or outside, just F equal to zero. You understand what I'm saying? So what is the tangential flow is that for a given contour, let's say F equal to zero, the tangential part is actually this. How does this point moving along with the tangential part? And the normal part is the 90-degree normal to it. Okay, so if you don't care about the tangential flow, your hardening law is actually just the speed functions. How do you find the speed function so that I can evolving it in the right way? And speed function is a scalar functions that are actually exist everywhere, just like the U functions. If you can determine the U functions as a functions of the internal variable, then you can evolving the plasticity in any different way or in any different shape. Okay, so actually, then you kind of combine the geometrical understanding and the plasticity theory with the level set, so they have a good marriage with each other for a given time. Okay, so the F should be the functions of the internal variable. The another nice thing about the shape speed function is that if you only have a scalar internal variable, you can consider, for example, the accumulated passing string as the artificial time, not the actual physical time, because the accumulated passing string are supposed to be monotonically increasing, just like time there's an arrow, and then you can actually solving the classical thing, and then using the t just as the internal variable, and then you can actually get an evolvement like this one. You start with one U surface, and then you end up with another shape. In this example, it's not easy to write Arden-in-law. At least I don't know how to do it. But if you're actually using a level set, you just need to use the machine learning to find out what is the speed functions after you obtain the initial U surface. So in terms of implementation, like what we talk about, if you do that, then the price you actually need to pay is that you actually need to know how to write parasiticity model. But if you already have the parasiticity model, the benefit you get is that you only need to make the change in the thing that I'm actually put it in the bracket. So if you have a return mapping algorithm, you only need to make a few change, and then you can obtain it, the change of it. It's actually a minimum surgery. And then for a different parasiticity model, you just actually need to you still need to come up with the hard internal variable that we will cover in a later class. But suppose you know the internal variable, what you actually need to do is actually you just need to evolve the f. And in that case, you also don't need to enforce a consistent, you don't actually need to put the hardening law there, because the hardening law is implicitly implemented in the level set. You just need to put the consistent functions and the passive corrector there, and then we'll compute the algorithm. So algorithm, from the algorithm perspective, if you already have the real-time mapping algorithm, it's actually very easy to implement. And you can see the flexibility here, like if I actually have, this is an actual polycrystal simulation. I have a polycrystal, I shear it in certain directions, and then I can actually break the symmetry of the piping from the data, and then I don't actually need to explicitly write the constitutive law. There are also benefits on using that geometrical representation of the U surface, in the sense that, for example, you can easily force the convexity. Okay, for example, if a material is new, convexity here have a following benefit. Let's say I have these 2 points that are in the elastic range. If I actually have a non-convex U surface, I draw a straight line between them. A linear combination of that elastic thing will suddenly yield, which is not good, or actually making complications. But in a convex one, I would actually never have that problem. Any linear combination between elastic string combination A and elastic combination B would remain in the U surface. Okay, so I get some geometrical benefit from it because I can explicitly enforce the convexity. Versus if I actually using the recurrent neural network, it will be very difficult to do it. Okay, and the convexity is very important to is one of the easy track to enforce the thermodynamic consistency. Okay, you don't want to create a negative plastic dissipations, or when you have energy dissipation, you don't want to gain energy. And that geometric track is actually so simple that you can just forcing the U surface to be convex, and that's it. That's the end of the story. You don't actually need to do any post-processing or funny business, or actually doesn't partition the elastic plastic part and doing it in the post-processing step. Okay, so yeah, and you actually, I would argue that you maintain the same flexibility of creating any parasiticity model. Okay, so you can see here as the level set theory allow you can evolve the U surface in any way you want. You can even cut it into 2 pieces, although it would make no sense. Okay, but it won't actually hurt the how general the parasiticity model is. So it's really I think that is actually the closest scouting key that we can think of, while actually still playing the same game of writing a lasso parasiticity model. Here you can see that the result are compared with the RNN or convolutional 1D are actually a little bit more robust, and it won't suddenly have this fall off the curve behavior. Okay, so why is that? Okay, you may still make the wrong predictions, but the regularity on the U surface that you generate prevent that you actually suddenly get this thing. It's really hard to get this. In order to think about that, this oscillating pattern are very easy to get in the recurrent neural network, simply because of how the memory is actually introduced. Okay, it's from fading the previous time step. So you can see that if for monotonic loading, it has no problem. For cycling, it's just start to have those buckling, because it's trying to pair that small piece of the loading and unloading together, and you have a sharp gradient, or you have very branch behavior in the loading and unloading pattern. So eventually it learned the wrong thing, and then it actually leads to this pattern. But here you can see the learning is actually not even that advanced. It's just a supervised neural network. But you can get a way more robust result. Okay, you may still get the wrong results, but it won't oscillate because you still have the elastic model, and your plastic U surface are actually sufficiently smooth, or more accurate to say, you can control the smoothness. You can actually using it for multi-scale simulation. This is actually a bar with some polycrystal plasticity, and then you can actually see that it's actually very close to real multi-scale simulations. You can also using this to actually customize the constitutive law for a particular polycrystal. Usually you don't design yield surface for a particular polycrystal, but just because of the neighbor cost. But if this thing is automatic, you can have an image direct to constitutive law approach. If you can obtain the image of the polycrystal, run a lot of simulations, you can actually create a custom polycrystal in any different locations, then you can capture more results. The extension to the hardening law, I think that now what actually happened before is the following. I'm going to use the geometrical inspirations to actually control all those different shapes, all those different kinematic. I just find the right combinations. You can see in that in the plasticity course, you first learn the isotropic hardening, and you learn the kinematic hardening, and you learn the combined kinematic isotropic hardening. You can do the same and then add the translations, rotation, add all those things. Kind of think about it like a robotic problem. I just need to assign a weighting on all those different machinery. But then that would be actually really hard to do something, anticipate something. Let's say if you have a shape that actually start, maybe just go back to this. That would be really hard to do something with yield surface that actually evolve like this, for example. Okay, which actually does happen. Okay, or when you have two crystals and they evolve in different directions. Like this one, you can actually have a loading in a different direction that have very different behavior, and this actually gives you the flexibility. The last thing I want to talk about is that if you actually have an isotropic plasticity, you can still use the piping to actually simulate the yield surface. However, you can think about it, what you get in the piping is just one incident. Okay, I'm fixing a particular orientation and I create a constitutive law. If I actually want to complete the entire constitutive law for each orientations of the crystal, I need a particular yield surface, and then I'm linking them together. You understand what I'm saying? Just imagine that I actually have a Drucker-Prager model. Basically, it's a circle on the piping, but it depends on the pressure. So you can actually stem those instants together and then actually try to compute it. That would be different than the parameterization strategy where I'm just trying to change each incrementations. I don't have a right answer for that, but I would still recommend that if you deal with polycrystal, you use the piping simply because you can see, I mean, just for very simple reason, you can see the symmetry a little bit easier. And when you rotate the principal axis of the polycrystal and run a new simulation, you can see evolve. So that actually can give you some intuitions of what is going on. So anyway, so I think what I actually want to cover is the following. This is actually the level set theory combined with the plasticity theory. This is globally, this is what it's about. If you don't know plasticity theory and you don't know level set theory, that can be a little bit evolved. But if you have to pick one, you need to learn the plasticity theory first, because the homework is only about perfect plasticity that have yield surface doesn't evolve, if I understand correctly, about the homework. Okay. And then we will talk about the revolutions. The revolution require you to understand the level set. But if you don't understand the level set, you just need to review what is plasticity. And I want to say one thing that actually hidden treasure or people doesn't emphasize enough, according to my own biased opinion, is that people doesn't, I think that a lot of time we have a lot of geometrical interpretations that help us think about the model, but that was not leveraged enough. but in some sense, okay, well, for Ronnie, I think he actually using it enough. I actually record that, but you can see that. But the important thing is the following. A lot of time when we come up with a material model, what you actually did is not come up with the equations. You come up with the geometry. Okay, the geometry give you the sense of interpreting the stuff, and understand the geometry is built in your brain is the most natural way to think about the objects in a way. So here I just mix a subset of the choice. You're welcome to actually change those choice and then create a different model. For example, I only use associative flow rule. Is it a good choice? Maybe or maybe not. It really depends. So, but I would like to think about the following. It will be easier, according to my opinion, if you actually write a model, think about the physical world, but also think about the parametric world where there's an object you want to manipulate, like making a sculpture or actually manipulating the shape. That would help you thinking the problem in an easier manner. Okay. And then the parametric space is like the piece of paper or the medium you want to build your object. Okay, so a supervised learning, ultimately, it only depends on whether you have enough point cloud and whether you have the parametric space and whether you actually build in the supervised learning correctly. There's not that much secret about it, in my opinion, unless you do a very high dimensional problem, then you actually need to think about all the different things. Even the loss functions have to be written in a different manner, but in a low dimension thing is not that difficult. Okay. Another thing I would want to say is that you need to think about whether the neural network is necessary. For some simple pattern, you can build a kernel. You can actually simply using a polynomial, and then that would be kind of meaningless to use the neural network. But so don't using it just because it looks good. And then anyway, so the last lecture and this lecture, I actually presented two different roles that are really diverge. I don't want to quote anyone, but I think the future is one of those. I'm not so sure what it is. Either the future would require less in detail knowledge and you just put it in some magic algorithm to make it work, or you actually need to incorporate some idea to simplify the problem as much as possible, and then you find the opportunity to use the right machine learning tools. So anyway, I guess this is actually what I think. But if you have different opinion, I would like to hear as well. So but I do think that the world is changing very fast. In particular, if you do the homework, you can actually see how much you can do with your ChatGPT and Frankenstein it together. So that would also be interesting. But I think that in order to write a model, you need to know the control. So I think in the analog that we talk about is like the difference between building the engine and driving. So in driving, in a constituted analog, you need to know how to manipulate all those ingredients. Okay, that would help you think. Okay, and manipulate those gradients geometrically. Okay, so next time we will talk about the involvement and the implementation details. And then after that, we will talk about how to write a hardening law that are related to the microstructure. So, okay, so any feedback or comment? I don't have an implementation section here in this lecture, but in the next one, we will have it. And then we will go for that lecture in terms of how to build the perfect plasticity in collab. And then after that, maybe a little bit of evolvement of the level set. And then we will move to our next topic, which is actually the real goal of the talk is sorry, not the talk. The real goal of this short course, the geometric learning. Okay, so far the level set kind of open the gate because you're still dealing with the implicit representations of the U surface, but there are other ways to represent the shape and size and topology and geometry, and that will be covered in February, hopefully. So okay, so I think that's it. Thank you.